Today we look at Newton's method, which is covered in our book in section 4.8. So Newton's method is an algorithm used to approximate solutions to equations by finding better and better approximations to the solutions or the roots or the zeros or whatever you want to call it of the function. And it's uses iterations, and it keeps going until you have the degree of accuracy that is required. So some things about Newton's method: applies to equations of any degree and applies to non-polynomial equations such as this, which is not easy to solve and almost certainly will need some sort of approximation technique like Newton's method. Works with systems of equations. So when I was in grad school, one of my professors had mentioned that he was on a design team back in the 80s when they were talking about that Star Wars missile defense system, and it ended up being determined that it's not really feasible. But the idea was, if incoming missiles from some other country were coming in, the Star Wars defense system would shoot them down. And the calculations were using systems of equations and were being solved using Newton's method. So it works with systems of equations also. And we'll see when we do this that without some sort of calculator or computer, doing these by hand is really tedious. There's a lot of tedious calculations, and the method will occasionally fail. But it's a very popular method. It has been for a long time. Many calculating devices use some sort of variation of this method. So let's take a look and see what this method is all about. Okay, now I sent you a file that looks better than what I'm looking at right now. So once again, the software that I'm using doesn't do a very good job of bringing these files in. So the picture's a little messed up, but we'll just try to make the best of it. Okay, so I've got a new picture in here, and not as pretty as the one in the handout, but it will work. So we are looking to solve this equation f of x equals 0. And we know if you have an equation equal to 0, graphically, you can interpret that as where the graph is going to cross the x-axis. So this is the root we're looking for. We want to know what number is that. So another way to say that is the solution. I'm just going to put this in here. I'm going to add this. This root that we seek, that root is the solution to f of x equals 0, right? When you solve the equation, the solution you get is where this graph will cross the x-axis. So we want that. So the way Newton's method works is we pick an initial point. They just call it an initial guess. And maybe we pick like this point right here. Maybe this will be what we'll call x sub 1. This is our initial guess. And so Newton's method is going to improve on that guess by doing this. It's going to figure out the y value there. So we give it this initial guess, and it figures out where that is here. You know, it could plug in x into the function to get this y value, and then it's going to take a tangent line to that curve. So it's going to take a tangent to this curve, which will then go something like this. We won't actually have two lines up here. Got the tangent line to the curve, and then what it's going to do, where this tangent crosses here, this is going to be our new guess, x sub 2. And you can see it's better, right? It was a better guess now. The error is less because the difference between these two numbers is much better. And then Newton's method will repeat that process. So now it's going to figure out where that is on the curve. It's going to take a tangent line to that point, and it gets really close, like our third guess is right on top of it. And you basically repeat this process until you get the level of accuracy you need. So to see how this could work, let's consider line L. And line L will be this first guess right here, this line L. So our initial guess. So we had this initial guess of x sub 1, and that resulted in this tangent to the curve, line L. And what we'll do is just think about algebra class. We had y minus y1 equals the slope times x minus x1. We've all seen that plenty of times before. And then let's just identify a few points on this curve. So this point right here, that point has a coordinate of x sub 1 and then f of x sub 1, right? So whatever the y coordinate, whatever the y value is when we plug x sub 1 into here. So that's the point x sub 1, f of x sub 1. And then let's also consider this point right here. So this comes down here. So the x coordinate is x sub 2 and the y coordinate is 0. So that is going to be x sub 2 comma 0. So with those 2 points, we can talk about this line L. So if we plug this in, remember the way this works, we have a slope and then the point x1, y1, x1, y1. Well, x1, y1 we can use right here. So we could say, okay, this is y minus f of x sub 1, right? Because that y1 is right here, x1, y1. And then the slope of this line, well, the slope is just going to be the derivative of that function at this point, right? Isn't the slope of this tangent just the derivative of that function evaluated at this point? So this is going to be equal to f prime of x sub 1 times x minus x sub 1. Because remember, we are plugging in x1, f of x1 into here for x1, y1. So that's why x1 is still x1, right? It's still the same. So now we're going to use the fact that this point is also on this line. So we know if this point here, x sub 2, 0, is on that line, then we should be able to plug this in for x and y, and we'll get a true statement. So we'll make a note of that real quick. We'll say, now use point x2, 0, which is the x-intercept of L. The x-intercept of this line L. So if we plug those in there, we're going to plug in x, y for x, y. Then we'll get this. We'll get 0 equals, or whoops, not 0 equals. Get 0 minus f of x sub 1 equals f prime of x sub 1 times x2 minus x sub 1. So again, we're using this, right? We're using this equation, but for x and y, we're plugging in x and y. So we get here. So I'm going to distribute through here a second. I'm going to distribute this through here. So if we do that, we'll get minus f of x sub 1 is equal to x sub 2 times f prime of x sub 1. It's f prime minus x sub 1 times f prime of x sub 1. So what we want to do is we want to solve this for x sub 2. I'm going to solve this equation for x sub 2. So I'm going to add this to each side. So we will get x sub 1 times f prime of x sub 1 minus f of x sub 1 equals x sub 2 times f prime of x sub 1. And now I'm going to switch these around but at the same time I'm going to divide by f prime of x sub 1. I just want to have x sub 2 on this side of the equation, so I'm just going to use reflection, just flip these, and also divide by this f prime of x sub 1. So if we do that, we will get x sub 2 equals, and we'll have x sub 1 times f prime of x sub 1 divided by f prime of x sub 1 minus f of x sub 1 divided by f prime of x sub 1. Right, so all I did, I reversed these. I put this side over here, and then I divided each side by f prime of x sub 1, which then will allow us to cancel this. And so we will finally get x sub 2 equals x sub 1 minus f of x sub 1 over f prime of x sub 1. And this right here is Newton's method. It gives us a formula. It gives us a formula for the second x based on the first x. All we need to do is know this first value. We subtract the function at that value divided by the derivative of the function at that value. And that'll give us x sub 2. And then it's an iterative process, so it just would go through again and again and again until the gap between the value you have and the real value is small enough to meet whatever tolerance you have. So if we were to continue this process, we would get the formula for Newton's method that you often see, which looks like x sub n plus 1 equals x sub n minus f of x sub n divided by f prime of x sub n. So this is like the general formula for Newton's method. So on the next page of the handout, you have that right here. You have the formula there. And we've got our first example. So we've got x cubed minus x minus 1 equals 0. And we want to solve it using Newton's method. Well, first there's a note that needs to be made. Every single time we use Newton's method, every time, we need a function. We need a function to use Newton's method. Actually, that's just an M. We need a function to use Newton's method. So what we can do is this. If we want to solve this equation, let's let this be f of x. And then we can figure out where f of x equals 0. So we're going to let this thing be f of x. So we'll say, since we need a function, so let f of x equal x cubed minus x minus 1. So to get started, we're going to need to take the derivative, and we're going to need to find an initial guess. So a lot of times you can just guess any number to get started, but sometimes there's more than one solution, and maybe looking for a particular one. So what we could do is this. This is something from earlier. We had this intermediate value theorem back in section 2.5, and I'm going to just mention something and see if you guys remember this. If I plug a 1 in here, I'm going to get a negative number, which is easy to see. I'm going to get a negative number. If I plug a 2 in there, I'm going to get a positive number. So if you remember the intermediate value theorem from section 2.5, it says if this is continuous, which it is, then it has to take on every value between f of A and f of B, where this would be continuous on A and B. So basically it's saying at 1 it's negative, at 2 it's positive, so there must be some number between 1 and 2 where it's equal to 0. So you may remember that, but we talked about that in section 2.5, so we can say by the intermediate value theorem from section 2.5. There is a number, we'll call it C, in this interval 1, 2, such that f of c equals 0. So sometimes you can do this. You know what you could also do? Sometimes people just graph that. So you could also just look at the graph of this to get an initial guess. Really, this isn't a huge part, so this isn't something we typically would have to do. You could just look at it and say, well, I don't know, it's probably a solution around 1 or 2, and just start with one of those for your initial guess. So in this case, let's just use 1. So just to get started on this one, let's use x sub 1 equals 1 as the initial approximation. And if we pick a different one, it's not going to matter, which we'll see. So here's our initial approximation. We'll say x sub 1 equals 1. This is our initial guess. Now we know 1 is not a solution, because when you plug in a 1, you don't get a 0. Right? When you plug a 1 into this function, you don't get a 0, so we know 1's not a solution. So to use Newton's method, we just have to find x sub 2. So x sub 2 is going to be x sub 1 minus f of x sub 1 divided by f prime of x sub 1. So let's write this over here. We've got f of x equals x cubed minus x minus 1, and we need the derivative. F prime of x equals 3x squared minus 1. So we are going to need to use these as we use Newton's method. So this one would give us 1 minus f of 1 over f prime of 1. And we get 1 minus, well, f of 1. If I plug a 1 in here, I get 1 minus 1, which is 0 minus 1. So I get a negative 1. And then if you plug a 1 in for the derivative, you get 3 minus 1, which is 2. So I basically get 1 minus 1 half, which is 3 halves. Okay, so we get 1 first. Our second guess is 3 halves. And I'll just do one more just so you can see. This is a kind of a simple equation. It still gets very tedious by hand. So x sub 3 is going to be x sub 2, which is 3 halves. So it's going to be 3 halves minus f of 3 halves divided by f prime of 3 halves. So Newton's method, what we always do is we look at the previous one. X sub 2 is the previous one minus f of the previous one over f prime of the previous one, right? And that's why we plugged the 1, because our initial guess was 1. Our second guess is 3 halves. So for our third guess, we're going to plug in 3 halves here, here, and here. And if you go through this, in other words, if you take the time to plug in 3 halves here and then 3 halves here, you'll end up getting this. You get this is equal to 3 halves minus, well, f of 3 halves is 7/8 divided by f prime of 3 halves, which is 23 over 4. And you get 31 over 23. So this is our third approximation. And that is equal to, let's say this is equal to about 1.3478. And I'll just do one more without actually doing the work. But if you went through the calculations here, so basically we're going to plug in 31/23, right? 31/23. We're going to go 31/23. Let me just to make it clear, let me write this. We're going to go 31/23 minus f of 31/23 divided by f prime of 31/23. You can see this would really be a nightmare if we really had to do this. We get about 1.3252. So this is our basically, I guess this is an approximation of our third guess and our fourth guess. And we would keep on going until we got as accurate as we wanted, which I'll show you what I mean by that when you do one of these on the calculator. But before that, let's see what could go wrong. What can go wrong using Newton's method? Well, a couple of things could happen. Let's say if f prime of x sub 1 equals 0. So think of like of what we were doing here. We had this situation like this, and we had, when we did it, here's our initial guess, and the derivative at that point was not 0, so it slanted down to get x sub 2, right? Here was x sub 1, here's x sub 2. But if you had some weird situation where, maybe you're trying to find this root and your x sub 1 is right here, and then your tangent line is horizontal, it's sending you far away. You'll never see it. Or even if it's not horizontal, but it's, tilted somewhat, it could still send you way, far away. So things like that can happen. So if the derivative is 0, the tangent line will be horizontal. Let me get this stuff out of here a second. It actually erases better than the real whiteboard. It actually erases. It will be horizontal. And you're also going to get division by 0. So geometrically, you have a horizontal line. Algebraically, when you try to plug in the formula for Newton's method, you're going to get division by 0. Or we could say this. I'm going to leave a little gap. Leave a tiny gap here because I'm going to mention something else. Leave a little gap, and then let's write this. We'll say if f prime of x sub 1 is close to 0, Newton's method may fail or work very slowly. So this is the one we just talked about. If it's not 0 but it's close to 0, it could send it way off. So this, I just want to emphasize something. These both look like only the initial guess, but it doesn't. It could be any guess. At any point this could happen. So I just want to point this out. We'll say the initial guess or any guess thereafter. For both of these. So in reality, this is pretty rare. We don't have this happen very often. And when it does happen, here's a little thing that will often correct it. So I'll say sometimes choosing another initial guess will correct this. So if you're using Newton's method and something really weird is happening, just pick a different initial guess. And a lot of times that will take care of it. So we've got this example on a calculator and got a video I'm going to try to put in here, and we'll see if it works, but it kind of walks through what we're doing. So if you want to use Newton's method on the calculator, it's really pretty nice on the calculator. We just have to store the function and the derivative in y1 and y2. So we go to y1, punch this in here, and then we store initial guess x sub 1 and x, and we'll go through this series, and this is where hopefully I'll be able to upload a video and make this work. Okay, so you've got this video here, and this will kind of walk us through it. So let's try this.
So we want to go to y equals and punch those functions in there. So in y1 is the actual function, and in y2 is the derivative of the function. So take a minute and plug those in. And then once you get done, what we want to do is store our initial guess in x. So to get out of here, I'm going to go second, quit. And then I want to store 1 in x, so I hit 1. And then use the stores in key. The stores in key, so hit stores in. Then I come up here and press X. And we're in function mode, and when you're in function mode, it's only going to pay attention to that X. So we hit X, then hit Enter, and now 1 is stored in X. So to get our next guess, we go through the iteration, so we hit X minus. Now we need to access the function and the derivative, which are in y1 and y2. So to get there, we press this vars button for variable. So you press vars, and we go over to y variables, and it's a function, so we hit enter. And y1 is what we want, so we select that. And now we're going to divide this by the derivative, which is in y2. So again, we go to the vars button, go to vars, go over to y variables, and again it's a function. Now this time we go down to y2, and hit enter. And then we want to store this in x, so we hit the stores in button again, stores in x, and then when we hit enter, it gives our next guess. And every time you hit enter, it'll rerun and get you a better approximation until eventually the numbers don't change anymore. So at this point, these numbers aren't changing. So if the calculator showed more decimal places, they'd be different. But as far as our calculator can display, they're the same at this point, so we can stop and see that that's the solution to x cubed minus x minus 1 correct to that last decimal place.
Okay, so that'll make it a little easier to see what this is talking about here. And then you can repeat the process with your initial guess of 2. And with initial guess of 2, you should get the same thing. And Newton's method is fairly fast, especially on a calculator, so it usually converges to the answer pretty quickly. So another kind of question we'll see sometimes is something like this. Find the square root of 5 correct to 9 decimal places using Newton's method. Well, we are going to need, I was looking for this note, it's way down here. So we need a function in order to use Newton's method. So here's how we get the function. Here is how we solve this problem using Newton's method. And sometimes students get tripped up by this. So make sure you're okay with this. We need a function. So here's what we do. We are looking for this, right? We want to find this x value that's equal to the square root of 5. So just always start off with this. And then what we can do is come up with a function that's equal to 0. So I want to get rid of the square root. So let's just say I square both sides. So I get x squared equals 5. And then if I subtract 5 from each side, right, subtract 5, I get x squared minus 5 equals 0. So this is the function we want. Because isn't it true that this is the solution to this equation? So just to make it clear, so this right here, this is the solution to x squared minus 5 equals 0. So because of that, we're going to let this be our function f of x. So if you had to find, say, a cubed root, you would cube both sides. So you basically just, for something like this, we need a function. So we build a function. And then once you have a function, we can use Newton's method to solve it. So we've got our function here, f of x. So I'm just going to write this off to the side. So f of x is x squared minus 5. F prime of x is going to be 2x. So we need these. And from that point, let's do this. I'll do a couple of these by hand first. So we have to pick the square root of 5. And we know it's going to be around 2, right? Close to 2. So let's just choose that as our initial approximation. So let's choose x sub 1 equals 2 as the initial approximation. Okay, initial approximation, a little bit of bad planning there. So we've got our first guess. Now we want our second guess. So our second guess, x sub 2, well, we know it's just going to be the previous guess put in a few different places here. So that's going to be 2 minus f of 2 over f prime of 2. Same as always, right? To find the next one, we look at the previous answer. We plug this in. So that would give us 2 minus. So I need to take this 2 and plug it into the function. So if I plug a 2 in here, I get 2 squared, which is 4 minus 5, which is negative 1. So you go minus 1 divided by. And then I plug 2 into the derivative. 2 times 2 is 4, so I have a 4 down there. So 2 minus 1/4 is 2 plus a quarter, so 2.25. So we started at 2, now we're at 2.25, and we should be getting closer to our approximation. So if we were to do this one more time, we would take 2.25 minus the function evaluated at 2.25 divided by the derivative evaluated at 2.25. And if we went through that math, we would get roughly 2.236, and then there's a whole bunch of ones. So that'd be our next approximation. And of course, what we would normally do is we use this on the calculator. So to do this on the calculator, we do just like before. We want to put this in y1, put this in y2, store 2 in x, and then walk through that same process with the last problem. And as you start off, if you store 2 in x and you run through the iterations, you should see these numbers come up as you go. And if you go far enough, it doesn't take very long before they stop. So we would say, if you keep going here, you'll get x is approximately equal to 2.236067977. So this is just using Newton's method. And then just to check in your calculator, now your calculator uses what's called the Cordic algorithm. The Cordic algorithm is also uses iterations, and it uses a lot of trigonometry in the iterations. Very human, unfriendly calculations, but it works great on a computer or a calculator. But just to verify, if I ask the calculator for the square root of 5, and it gives me exactly the same thing. The calculator agrees with this using the Cordic algorithm. So this brings us to example 4. Never know what I'm going to get as I scroll up here. Okay, here we go. It showed the graph, so that's good. That's good. So find all the solutions to this equation. This is actually, I believe this is number 22 in our book. But we can see we've got this equation that equations involving trig and algebraic functions are really difficult to solve. They almost always have to be solved by some approximation technique, such as Newton's method. So what we did here is we just kind of tweaked this so that we could get a function, right? Basically set this equal to 0. So subtract x squared and add 2 to each side to get this set equal to 0. So here's our function, right? So we've got our function here. Then we need to take the derivative. So using this, we've got f of x is equal to sine of x minus x squared plus 2. So then f prime of x is going to be equal to cosine of x minus 2x. So those are what we're going to need to use. Make sure you're in radian mode in your calculator, because when you evaluate these functions in your calculator, y1 and y2, you're going to want to make sure you're in radian mode. So this shows the graph of this in the standard viewing window. And so it looks like there's solutions around -1 and 2. And then it just mentions in the notes that we could have used the intermediate value theorem, which we were talking about earlier. That's the one from section 2.5. Right, so we could figure out by plugging in numbers, plug numbers in here until you get a positive number and then a negative number, and you know the root is between there somewhere. But this is just another way to do that. So we know there's roots around here. So for this one, what we would typically do in class is I would start off, we would say, let's let, you need a little more room here. So I would say, let's let -1, let's store that in x. And if you do that and run through the iterations, you get about -1.0615497775. And that would be for that root. And then for this root, we typically we store 2 in for x, run through the iterations. And again, these iterations depend on us putting this in y1, right? F of x goes in y1, f prime of x goes in y2. And then do the same process that I showed on the video. And when we store 2 in for x, what you should get for a solution is x is approximately equal to 1.728466319. And you could also, just check. The calculator should get the same thing if you graph this in your graphing calculator and you go to find the 0, command you might have used in algebra or from time to time to solve. You should get the same numbers here. So with these, you just have to go through those same iterations, starting from these 2 start points, and we should get here. And then we've got one more example. And this is the cubed root of 30. So this is when I had mentioned that usually these give us a little trouble because students would be, well, where's the function? Well, we have to make the function, right? So the key here is this. I'm going to put it in red. Remember what red means? Danger. Caution. We need a function, right? Need a function in order to use Newton's method. I keep making it capital. Okay, in order to use Newton's method. So we just make one up. So we want the cubed root of 30, so we create it by saying, let's say x is the cubed root of 30. And then we're basically going to come up with the function whose solution is this. And to do that, from here we would cube each side. So we would get x cubed equals 30. Then we subtract 30 from each side. And we get this equation. And you can see by just how we did this, the solution to this, or at least one of them, is this right here. So this is f of x. So if we were going to solve this one, in y1 we would put x cubed minus 30. And in y2 we would put the derivative of that, which is 3x squared. And then you just pick an initial point. You can even just experiment, put a number that's way off, like 10. And it should still, in most cases, converge pretty quickly. Probably a better guess, if you try this one, would just be like 3 or something. 3 stores in X. And we do the same thing as before. Right, and then you just keep hitting enter, and you should get the cube root of 30, and it should agree with your calculator of the cube root of 30. So this is the last section for chapter 4. So I know you guys know that means some good news coming. There's a test coming pretty quickly, which we will talk about very soon. But try this section out. It typically isn't too bad of a section, especially after like 4.7. But try it out and let me know if you have any questions.